Swayam Prabha. Digital India. Educated India.
Discussing this Langevin equation and Brownian motion. We started with this concept of correlation function. So, I will just kind of write that again. So, I mean there are different ways of visualizing it, but essentially the correlation function tells you is how much time it takes for a certain correlation to decay, and correlation is in terms of maybe a position correlation, velocity correlation, whatever correlation you can think of, right, or a force correlation as a matter of fact. So, what I was trying to show the other day pictorially, if you would try to imagine the signal A of t as a function of time t. So, this is t, right, and suppose you have a signal says something like this. It is a fluctuating signal. So, I am taking only a small portion of the time t, right. Now, what I do is, then after a certain time, say t correlation, this guy say now moves to, let me see whether I can get a better idea of this. So, this is the maximum. So, now this moves to this after a certain time t. So, that means if I do like this and if I get this, then this is your t correlation. Okay. Then what I do is I go for another time, So, now what will happen is, I will just build on this. This signal has shifted further from where it started. Okay. So, what you can look at is a couple of things. If this is your if this is your max of the signal, right, I can see at subsequent times. So, this is a ladder correlation time, right. So, this is even a longer correlation time. Okay. So, this is what should I say. So, this is another correlation time t correlation, say 2 greater than t correlation, which is written out here. So, this is 1, I can write 1 out here. So, what I was then trying to develop was, if you take this value a of t, say a of t naught, say this is t naught, so this is t naught at one time, and then a of t plus t naught plus t correlation. That is what we are trying to look at. This is the correlation function, this is the product of two signals at shifted by a certain time t correlation. So, you can immediately see what happens when t is very close to t naught, right, when t is very close to t naught. So, that means t correlation is really small, right, then essentially a t 0 plus t correlation is almost equal to a t naught, right, and that is what we said last time. So, this means this would be equal to, so that means I can from here I can get a square t naught. But remember, when I am taking t naught, so this is the maximum I can have of the product of these two. Now, what will happen is, if you keep this t naught the same, that means if you keep this time the same at what you are observing, after a certain time this guy has moved out a little bit. Now, you look at this portion, now you look at this portion, this guy. So, automatically what will happen is, if you now take a t naught, which is this one, times this, which is a t naught plus t correlation 1, then what has happened? Because it has shifted, the value at that time, which is here, has come down. So, the product has what? Decreased. Now, you go to a further time where you can see it has moved farther away. What has happened here now? This a t naught plus t correlation is even lesser, and hence you are looking at a decay, right. So, this is what your correlation decay is all about, this is what you are correlating. This is one of the ways we can try to think about in terms of a signal coming out. Okay. So, that was again a correlation function. I just thought I would mention it to you again, if this is possibly one of the ways you can try to visualize it. Now, last class we were also developing this, that we were looking at the velocity correlation function, right. And when we were looking at the velocity correlation function, we derived this relation, where the ensemble average of the correlation, that is the product of v at 0 and v at time t, is equal to, we had v square at 0, then e to the power minus xi by m times t. That means, your correlation function is decaying exponentially, okay. And we also drew a graph for this, and what we said was, if this on y axis, if we have v 0 times v of t, this is what we have on the y axis, then the maximum would be what? Would be v squared, right, and then it would slowly decay. So, this maximum value is obviously v squared 0, right, and then it decays based on the equation v square 0 e to the power minus t by tau. This tau I said was tau correlation, was not it? Said was tau correlation, where tau correlation is equal to, what was tau correlation equal to? M by xi, and because the power, or because the factor in the exponent has to be dimensionless, then if you already have time t, then m by xi should be having also the time of t, I mean the units of t, right. So, it is a correlation time. So, this is essentially decay time. So, what does tau correlation say? Tau correlation says, what tau correlation says is, I can write this, tau correlation says is, if this is tau correlation, it will tell you, or this is the time at which correlation decays to 1 by e of its original value. Okay. So, again tau correlation, or what is m by xi, or tau correlation, is that time at which your correlation signal decays to 1 by e of its original value. That is how tau correlation is defined. Okay. Now, having seen all these things, we can simplify our equation a little more. Now, before I move forward, can someone tell me what should the number of this equation be? 5 or 6, something like that, right? Just check, what was it last? So, this would be 5. So, this was 5, right? Okay. So, we will keep it at 5, and then this one, what do you see? I will name it as 6, because I have introduced this tau correlation. Okay. But now look at this, can we simplify it further? Well, now what do you mean by simplification? From equipartition principle, if you remember, half m I can write v square 0 should be equal to what? This is from equipartition, right? This is from equipartition principle. So, this should be equal to half k T, where k is the Boltzmann constant, T is the temperature, right. So, then you can replace V square 0, the ensemble average, by k T over m. Okay, you can replace it by k T over m. Now, after having done this, then your actual equation becomes T is equal to k of T over m e to the power minus T by tau correlation. This is 7, where tau correlation is equal to m by xi. So, this is one of the most simplified expressions you can have for a velocity correlation function. Okay. And what it says is, if I start with the velocity v 0, then how much time does it take for this initial memory of the velocity v 0 to be erased, right. That is what Brownian motion can do to you. It can randomize your initial velocity you start with. So, if your time is, this is what we wrote down in last class, at the very last portion of the class, at the end of the class, if your time is less than tau correlated, then you still have correlation between your initial velocity and the velocity at that time. But if you are much beyond tau correlation, then what has happened? Then that v 0 and v of t, where t is much greater than tau correlation, there is almost no correlation between these two. Okay, they are almost not related with each other. Good. Now, if you do a small integral, say 0 to infinity, okay. So, what I am doing now is v of 0, v of t, d of t. Now, what should I get? So, what I do is, because I know the function form of this, the equation of this, then I can write 0 to infinity k T over m e to the power minus xi by m t d of t. Okay. I have moved out tau correlation, I have just put in the actual one I had, xi by m. So, if this is what we have, now tell me, k d by m is a constant, is not it? Okay. So, k of t over m, then what should come out on the other side? On integration, it is between 0 to infinity, what should I get? Should not I get this? So, it is between 0 to infinity, right. When t goes to infinity, what happens? That exponential function anyway goes to 0, that is 1, and then when t goes to 0, the exponential function goes to what? 1, and then you have a negative sign out because of minus xi over m. So, then you get this m xi, because 1 by xi over m gives you m xi, that is how your coefficient comes in. So, what you get is something which you had, or which we had derived before. What is this? Is not this d? Remember, this is what we did when we talked about the Einstein-Smoluchowski equation or derivation, right. See, this is, that was separate, this is separate, but see, d is a fundamental quantity, right, and hence no matter what you do, no matter what direction or what approach you take to derive d, you should be ending up with the same value, and this is what you get. Now, it makes sense. Diffusion is related to the movement of a particle, hence related to the velocity. So, if you would take the integration over all time of this correlation function, you would get the diffusion constant. Okay. Now, that is not the only thing, there is one more important aspect. Your d is a kinetic property, is not it? It is related to diffusion, it is a kinetic property or a transport property, it is a transport coefficient. Now, what about this v 0 and v t? This is an equilibrium correlation function. Remember, I am taking on ensemble average. So, it is an equilibrium correlation function. So, what this relation or what this integration has done for you is, it has related an equilibrium correlation function to a kinetic property or a transport coefficient, which is the diffusion coefficient. So, if I write it, so we have related equilibrium correlation function with a kinetic property which in this case is the transport coefficient or the diffusion coefficient d, and we can say this or the equation, say the equation we just derived. So, 0 to infinity v of 0 v of t d of t is equal to d, this equation I can, what will the number be, 8. So, if this is 8, then this is an example of something known as Green-Kubo relation. The Green-Kubo relation. Okay. These two are mathematicians. Have you heard of Green's function? In mathematics there is something known as Green's function, and there are also Kubo's relationships. So, they combine to give the Green-Kubo relationship, and this is what it is. So, the basic idea of this Green-Kubo relationship is it relates an equilibrium property. Equilibrium property is what? Thermodynamics to something which is kinetic in nature, in this case the transport coefficient T. That is what your Green-Kubo relationship tells you. Okay. Now, remember velocity is a vector quantity. Okay. So, if I would do this, instead of taking this equation 8, what I would do now, I would say is, if I would be doing this integration v 0 v t, but here these are vector quantities d of t. Now, without doing any actual calculation, can you tell me what we should get? Keep this in mind, v 0 v of t, when v's are vector quantities, then what is v 0? So, v 0 is essentially equal to v 0 x times I plus v 0 x y times j plus v 0 k, the all I j k being the unit vectors. The same thing will happen for v of t. Now, when we take the dot product, which are the ones which only stay? The I, the k k and the j j. So, what you have is essentially v I, v 0 I, v t I plus v 0 j, v t j plus the other one. So, what do you have? D plus d plus d. So, this should be equal to what? 3d, and that makes sense, right. So, that was only one dimension we talked about, and this you are talking about taking velocity to be a vector quantity, you are talking about the 3 dimensions, and this is the actual expression for d, or we can write d is equal to 1 by 3 0 to infinity v 0 v of t d of t. Now, this is an important relation, we can put this as equation 9. Okay. So, there is one more example of Green-Kubo relation. I will just write that, we will not go into it, but this you should also at least try to appreciate. If I have a friction coefficient, the xi, remember the diffusion coefficient was related to the velocity, and that made sense. Now, what do you think the friction coefficient would be related to in terms of a correlation function? What is friction related to? Well, I am talking about the nature. Diffusion was related to velocity with the speed of the particle. Now, friction would be related to what kind? Would it be speed? Would be force? What? It would be force, isn't it? So, then just based on that premise, what I can write is d of t. So, this is what your friction coefficient is, how it is related to your, this is your force correlation function, okay, because friction is related to frictional force, that is what a friction coefficient is, and that is why it is related to the force correlation. Okay. This is another example of your Green-Cover relationship. Okay. So, that is what we had to discuss about in terms of a correlation function, and again remember, if anyone would be doing any molecular dynamics simulations, right, they would always, along with these, along with many other things, one of the very important parameters they always look for is a correlation function, okay, and that is what you have just seen. Now, not only in molecular dynamics, correlation function is omnipresent in whatever you are talking about, because the moment you have Brownian function or the Brownian motion, you are going to have a correlation function. You would always want to know, if I start with this value, under what conditions or at what time under the given conditions would my correlation decay, to what extent, right, and this is the most general form, that is what we looked at. One was the velocity, we can do it for the force, but anyway the velocity itself gives us a decent amount of idea. Okay. Now, before ending the last class, we also I also told you something. The other important, see, this was in terms of correlation function, but when we are talking about motion, when we are talking about displacement, there is a very important parameter we talk about, it is called mean square displacement, right. Now, can we get an idea of the mean square displacement from Brownian motion or from the Langevin equation? Now, again, see, all these things you know, all these things you know. For example, Brownian motion, it is a random motion, right, but then how do you visualize random motion? The way to visualize a random motion is to see how fast that correlation decays. So, that is one way of parameterizing, or that is one way of visualizing what a Brownian motion is. That is number one. Number two is, if I am going to have a mean square displacement, would I be able to derive the expression for mean square displacement from a particle starting from the most general equation I have, which is the Langevin equation, because we said the Langevin equation is a force equation, we should be having all informations, that is one of the most general equations we can have. So, can we do it in a similar way, right. So, let us try to do the mean square displacement and see how far we can go. In this class. So, to look at the mean square displacement from the Langevin equation, obviously we have to start with the Langevin equation. So, the Langevin equation was m dv d of t is equal to, there was a function which was f of t, then there was another function which was what, xi times v. Okay. Now, what is v equal to in terms of a displacement of a particle? Velocity is equal to dt. Okay. So, now what I can write is, I using this v is equal to dx by dt, in this equation I can write m d of dt dx by d of t is equal to f of t minus xi dx by d of t. Okay. I just put in the expression for velocity in terms of the displacement, and why do I need the displacement? Because I am looking not for the velocity in this case, right. The previous case I was looking for the velocity correlation, but here I am not looking for the velocity anymore, instead I am looking for what, the displacement. So, I have to put in x by some way or the other. Now, so I can write is, so this would be d2x over dt squared. Instead of doing that, can I write this as, what should I write it as, m then x. So, this is what, this is f of t, okay, minus xi, I can write as x dot, is not it, I can write it x dot, no problem. Okay. X dot is the, what does x dot signify? X dot signifies it is essentially dx over d of t. Okay. So, this one I can write d of x dot over d of t, because that is what we wrote down. So, let this equation, because I am starting with a new topic, let this equation be 1. Now, what we do is, remember we are talking about displacement which is x, it is not x dot, because x dot is the rate of change of displacement. So, what I do is I take this equation, I multiply throughout by x, right. So, that means multiplying 1 by x, what I can write is m x dx dot over d of t is equal to x f of t minus xi x x dot minus xi x x dot, and this would be equation 2 for me. Okay. I have to solve this equation. I will also have to take the ensemble average. Now, before doing that, let us look at this. How can I write x dx dot by dt? So, for example, if this is x dx dot over d of t, can this be written as d of dt x x dot minus x dot squared. Can it be written like this, right? That is what I am going to write it like. Do I need to show the proof, or do you realize it will be written like this, right? So, you can see d of dt x x dot, it is a uv function, right. What are you going to be left with? So, this one would give what? So, this one would give two things. So, the first one, if you take this, so it would be x dot dx dt, right. Then what would be the next one? X dx dot over d of t, right, and then you already have minus x dot squared. So, what is this one? This is x dot squared, right. So, x dot squared cancels out, and you are left with x dx dot over d of t. Okay. So, that is a simplification, or that is one change we are putting through, right. So, now having said that, so what now I can do is, so let this be say maybe 3. So, then I will use 3, in 2, and what I will write is m d of x x dot d of t, okay, and that is what I replaced it by, minus x dot squared is equal to f of t minus xi x x dot minus xi x x dot. So, this let this be equation 4. I have mixed an x out here. Let this be equation 4. Now, what I do is take the ensemble average of 4, that means all the parameters in 4, whatever you have, all the terms in 4. So, this would then become m d of dt, the ensemble average of x x dot, okay, minus m the ensemble average of x dot squared would be equal to the ensemble average of the product of x f of t minus xi, then the ensemble average of x x dot, okay, and this is equation 5 for me. Now, see what you already have. You already have an equation where you see this x x dot, you already have that x x dot. Maybe we are looking for a differential equation where we have to solve for x x dot, okay. It is like dy over dx, where y is equal to x x dot, the ensemble average of it. Now, before even doing that, or before even trying to realize what that gives us, can we do further simplifications of this equation? Can someone tell me? For example, what about the force term on the right hand side? Remember this, good. What we are saying is, because when we did the velocity correlation, we said that your initial velocity was not correlated with your fluctuating force f of t. So, here we also take what? Your initial position is not correlated with f of t. So, then what I can write is, based on a discussion from before, I can write x f of t is equal to f of t, because these two are uncorrelated. Now, what is average of f of t? That is, so this is 0. So, that means the whole thing goes to 0, because the average of your fluctuating force or the random force is 0. Now, one more thing, this is again from the equiparation principle, right? What did we say? Half m v squared, half m v squared is equal to half k t, right? What is v equal to x dot, isn't it? So, I can write half m x dot squared is equal to half k t. See, do not I already have an x dot square in my equation? So, then like what we did for the velocity correlation function, we are doing the same thing for the displacement. So, that means what I have is x dot squared is equal to again k t over m. So, if I say this is, what should I say, this is yeah, this is 6a and this is 6b, okay. This is 6a, right, and this is 6b. So, using 6a and 6b in 5, using 6a and 6b in 5, we have m d of dt x x dot, now minus m x dot square, this is equal to what? Good. So, this would be equal to minus k t, should be equal to minus xi x x dot, okay, or further simplification gives me d of dt x x dot m plus xi x x dot is equal to k t, or d of dt x x dot plus xi by m x x dot is equal to k t over m, and this is equation number 7. Okay, so, this is a differential equation finally we have to solve. You can see we started from something which did not look that pretty, okay, but at least we have something now which follows a set of rules which you use to solve differential equations, right. Now, hopefully, you have the handout that I gave you last time. You can see, look at the second one which talks about what? The integrating factor, right. Look at the second one which talks about the integrating factor. So, this equation number 7, equation 7 has to be solved using the integrating factor concept. It is a linear differential equation, first order, okay. This is the general form, is the general form of such an expression is can be written as dy d of x plus p of x y is equal to q of x. I guess that is what we have, right. Okay. So, dy dx is y prime, and if you are going to solve it, you take an integrating factor where you say y of x is equal to e to the power P of x d of x. Now, if you compare this with the one you have, what is your y? Your y is your ensemble average of x x dot, and what is x? X is t in this case. Okay, that's the only difference you have. That's the only change you have to make. Otherwise, everything is exactly the same. Okay. Now, Px is also defined for you, Qx is also defined for you. So, here finally, the solution becomes y is equal to 1 by I of x, then I can write integral of I of x q of x dx plus c. So, this is the final solution we are going for, okay, in terms of the integrating factor technique. Okay. So, let us do it just one by one. If this is what the form is, what is I of x for me? So, now well, let us do this. Instead of what I do is I say y is equal to x x dot, and in my differential equation say where dy by dx plus p of x y is equal to q of x, I take this x to be t. Okay, I take this x to be t. Now, I of t essentially is what is e to the power p of x. Now, what is p of x for me? So, p is what? Xi by m. Okay. So, xi by m, xi by m, then what I have there? D of x. So, it should be what? dt. Okay. So, what do I have then? This is equal to what? E to the power xi t over m, that is what I have. Okay. Now, put into this equation, the final equation, the integral of I of x q of x. Now, what is integral of I of x q of x dx for me? This is essentially I of t q of t d of t. I already know of what I of t is because I have got it here. This is I of t for me. Okay. What is q of t? Q of t is k t over m, isn't it? So, then what I can write is based on what I have. So, this is, well, this is essentially I of t because my variable is t out here. Then I of t q of t d of t is equal to, the first one is what? E to the power xi t over m, and what is the next one? K t over m t of t. Okay. And this, if I do the integration, I have k t by m, I have k t by m, right, e to the power xi by m t d of t. So, what do you get here now? So, k t by m times m by xi e to the power xi by m t. Yeah, so c is already there, you can see in the final equation c is already there, plus c, exactly, that is where the c comes from. So, c is already there, absolutely. So, I am just not writing c again. Okay. So, see, using this integrating factor you have already almost solved this equation, right. So, finally, what I can put in now is this is k t over xi e to the power xi by m times t. Okay. Now, look at this. When you are talking about a diffusion or when you are talking about displacement will be related to how fast or how slow it can diffuse. So, again it is logical that I get something which is k t by xi, which is what? My diffusion coefficient again. Okay. So, that see this again crops up. Okay. So, looking for the final solution, I should be having well, what was my y? Well, my y was x dot. Now, this should be equal to what? I have, which is the first one. So, one would be, okay, one would be what? One would be c, right. So, I should be having e to the power 1 by I t, which is this too many things, 1 by I of x, which is 1 by I of t, which is e to the power xi by m t, right. And then I would be having I x times q of x, right, which is we just derived, which is what, k t by xi e to the power xi by m t, then I would be having a constant c. Okay. So, then my x dot is equal to k t by xi plus the constant c e to the power minus xi by m t. Okay. So, this is the differential equation which we were started with, and this is the solution of the differential equation where y is equal to the ensemble average of x dot. Okay. So, this differential equation describes the motion of a particle undergoing, so not undergoing, under the action of a random force, which in effect is the Brownian motion. So, this is typical the differential equation you solve. Okay. So, if you would want to describe a particle exhibiting Brownian motion, then starting from Langevin equation, this is an equation you get. This equation is characterized by your displacement x, the rate of displacement x dot, the friction coefficient xi, the Boltzmann constant, which is a constant obviously, then T, the temperature, and obviously you have T, the time, the small t, which is the time. So, all these factors come in because Brownian motion is about correlation time. So, you should be having a sense of time involved. Brownian motion would depend upon how fast you do the motion, which is going to depend upon your friction coefficient xi. So, that xi is also involved. You increase the temperature, what will happen is you will change the speed or you will change the rate at which the displacement occurs. So, the temperature T is also involved, and you have the most fundamental things that you can think of in this equation. That is why this equation is so general for a Brownian, for a particle exhibiting Brownian motion. Now, only keep this in mind that the only force I am talking about is a frictional force, but if you would be putting your particles under other forces like electrical gradients, electrical forces and all these things, then those things have to be added onto it, and those become special cases, right. But this is the equation you always start from, and then you build upon it. You go on adding terms so as to take care of whatever situation, whatever force you might, external force you might think of. Then possibly you apply your steady state condition and try to get a relation. Okay. Right. Now, how do we solve this equation? Now, the way we solve this equation is, we again remember we are always going for displacement, and when we are talking about displacement, we are not talking about only displacement, we are talking about a mean square displacement. So, mean square displacement is average of x squared. So, I have to bring in x squared somehow, right, and if it is a mean square displacement x squared, then the root mean square would be that average of x square, the square root of that. Okay. That is what all of us are most familiar with, right, from the kinetic theory of gases. So, going for this mean square displacement, this x dot, this x dot, right. Now, this I want to replace, that means I want to replace x dot. How can I replace it? Can I write this as half okay, say d of dt x squared. Tell me, can I write it like that? What is d dt of x squared? It should be x dx over dt, right? I will be having a 2 out there. Okay, so that will essentially give you what? X dot, and the 2 is taking care of that. Is it clear to everybody? Huh? So see, by doing this, what we have done is we have brought in what? The mean squared experiment x squared. Okay, that's what we wanted. Okay, so then I can go back to this equation I did not name, right? Did not put a number. What do you think the number would be? 7, 8, 9 something? 8? Okay. If I put this equation as say 8, then using this in 8 we have half d of dt x squared is equal to kt over xi plus c e to the power minus xi by m times t, and this would be 9. Now what I do is I try to solve for c. So what I take a condition is at t equal to 0, x is equal to 0. So I can take any value of x, it does not matter, I can take x is equal to x naught, any constant. What I am saying is that when my time is 0, the displacement of the particle is 0. Okay. So if that is what it is, then if this is 0, if x is 0 at t is equal to 0, this one goes to what? This exponential factor at t is equal to 0 goes to 1 because this is 0. So I am left with c, x is 0, right. So this on this side we have 0. So then c would be equal to minus kt over xi. Okay. And if that is what we have, then I can write half d of dt x squared is equal to kt by xi 1 minus e to the power minus xi by m into t, or d of dt x squared is equal to 2 kt over xi 1 minus e to the power minus xi by m t. Okay. Let this be equation number 10. Okay. So this is more simplified than the other one because now you have actually put in the constant c. But see, the problem is we have not yet been able to find x squared, isn't it? Why? We still have a derivative of x squared. So what do I do now? It's simple, we integrate with respect to time. So integrating both sides. So what are the limits now? One is t is equal to 0 and the other one is t is equal to, okay, t is equal to infinity, because we are looking at very long times, right. What happens at the very long time interval and also at a short time interval, that is what we will look at. What will happen to x squared? That means at t is equal to 0, what should I take x to be? I can take x to be 0, right. That is what we started with. Okay. Then at the other limit I can take x to be equal to x. So then on this side on this side, on the left hand side, this is what I am going to have. On the left hand side, what I am going to have? I am going to have x squared only, isn't it? Is that clear? I am going to only have x squared. Now, here, instead of doing t is equal to infinity, what I will do is I will do is from 0 to t. So, I will just say t is equal to t. What we can do is, after we have the general equation, you can easily replace t by infinity, right, that we can always do. So, there what I do now is, if I do the integration, then I would be having 2 k t xi. Now, what is the first term going to give me? Remember, we are integrating between 0 and t. Okay. So, the limits are t is equal to 0 to t is equal to t. So, this is the lower limit, this is the upper limit. So, here the first one would be t, right. Okay. Now, what about the next factor? You tell me. Okay. Then what should I have? The first one you have 2, right, is 0 to t. One is e to the power minus xi by m into t, that will stay. What about the other one? That will go to 1. So, what should I have now? I should be having 1 minus e to the power minus xi by m t. You guys are okay with the integration, right? Or do I need to write it? You are okay with the integration, right? You are just integrating from 0 to t. The first term obviously is t because there was 1, integration of dt gives you t, right. Then I took m by xi, obviously it came out as a constant, it was a definite integral 0 to t. When you put t is equal to 0, you get 1, and I have taken care of the sign accordingly. Okay. So, this is the final equation describing Brownian motion, describing Brownian motion. Okay. As someone pointed out, that if I have, what should the ideal limits be? 0 to infinity. Okay. I am not taking infinity, as I said, but now I can make an assumption. What I say is, I will come back to this in the next class, but I will just I am trying to realize this. If I take t to be much greater than m by xi, what will happen? See, m by xi is also time, it is t by tau, which is tau is equal to m by xi. If I take t to be much greater than m by xi, what will happen? If t is much greater than m by xi, then this guy goes to what? Okay. If this guy goes to 0, then what am I left with? So, this is gone, right. Okay. So, what will we have? T minus m by xi. Okay. But we have already said that t is much greater than m by xi. Then what will have? T minus m by xi will be almost equal to t. Okay. Then what will we have? It will be 2 k t by xi times t, which would be equal to x squared, isn't it? What is 2 k t by xi? D. So, x square at very long times, that means t is much greater than tau correlation or t correlation, is equal to 2 times d times t, right, 2 times the diffusion constant d times t. Then what about the root mean square displacement? It would be root over 2d times t. Okay. I am not writing this one, I am just explain it to you, because we will do it in the next class on Monday. So, if by taking t is equal to infinity, that not t is equal to infinity, in that sense what I am saying is t is much greater than m by xi, you have x square to the power half, or root mean square speed is equal to root over 2 d times t. What it says is that your root mean square speed for very long times is proportional to the square root of t, that means the square root of the time that is involved. This is a typical feature, exhibited by a particle undergoing Brownian motion, I would show you a few slides on where you start assuming Brownian motion, you start assuming a random walk model, and then you also get the same expression. Okay, these are absolutely two equivalent expressions you get, you exactly get the same expression featuring the Brownian walk of a particle. What you should also try to do is, one case was t is much greater than m by xi. Think about what will happen if I take t to be much lesser than m by xi. See, t much greater than m by xi means that I almost have no correlation, isn't it, because t is much greater than tau correlation. That means I have lost all information almost that I have started with. So, the moment you have lost all information, that means you have erased all the memory. So, that is how the root mean square displacement or speed of a particle, displacement of a particle changes. However, if t is very or much lesser than the correlation time m by xi, then what will happen? Then what will happen, you will see, is that it will not depend upon your friction, all these things. It will depend upon something which you can figure out and we will look at in the next class. Okay. But anyway, again try to keep this equation in mind. This is one of the most important or fundamental equations that you can have for a particle exhibiting Brownian motion, right. I am sorry that the derivation took so long, but it is worth doing a derivation to try to realize that how you can actually come across and try to characterize Brownian motion of a particle. That is, if someone asks you what is the Brownian motion of a particle, what you say is that its displacement or root mean square displacement should vary as square root of t. If it does not do that, then the particle is not exhibiting Brownian motion or random walk. This is a characteristic criterion of a particle.